Module 3. Specialized welding processes and applications. Submerged arc welding saw and Electroslag welding ESW. Welcome to Module 3 and the course on submerged arc welding saw and Electroslag welding ESW. In this lesson, we will be exploring the fundamentals, equipment setup, operation, advanced techniques, and safety measures for two critical welding processes, submerged arc welding saw and Electroslag welding ESW. Whether you are a seasoned professional or new to these methods, this comprehensive guide will provide valuable insights and practical knowledge to enhance your welding proficiency. SAW and ESW process fundamentals. Introduction to submerged arc welding saw. Submerged arc welding saw is a highly efficient arc welding process that produces sound welds with minimal exposure to harmful radiation. It involves the formation of an arc between a continuously fed electrode and the workpiece, which is submerged under a layer of granular flux. This flux provides a protective barrier against atmospheric contamination and stabilizes the arc. Principle utilizes a consumable electrode and a continuous flux supplied to shield the arc and molten weld pool. Mechanism: the arc is struck beneath the flux, forming a weld pool that solidifies into a strong weld bead. Applications commonly used in shipbuilding, pressure vessel fabrication, and structural steel construction. 3.1.3 Equipment setup and operation. Power source often employs DC power, but AC can also be used for specific applications. Welding head houses the electrode holder and flux delivery system. Adjustments allow for precise control over welding parameters. Flux must be dry and clean, handled with care to avoid contamination. Electrode continuously fed into the weld zone. Available in a variety of compositions depending on the material being welded. Travel mechanism: automated systems ensure consistent travel speed and weld quality. To operate SAW successfully, ensure proper alignment of the workpiece, adequate flux coverage, and correct parameter settings, including voltage, current, and travel speed. Regular monitoring and adjustments are essential for optimum results. Advanced welding techniques and safety. Tandem saw employs multiple electrodes for higher deposition rates and faster welding speeds. Narrow gap saw suitable for thick sections, providing a reduced bevel angle and less filler material consumption. Pulse saw enhances control over heat input and weld bead shape, reducing the likelihood of defects. Safety in SAW: personal protective equipment (PPE), use of helmets, gloves, and flame-resistant clothing is mandatory. Ventilation: ensure adequate ventilation to prevent inhalation of fumes generated during welding. Electrical safety: use insulated tools and adhere to lockout, tagout procedures when servicing equipment. Introduction to Electroslag welding ESW. Electroslag welding ESW is a vertical position welding process that is highly efficient for welding large, thick sections. It uses an electric arc to melt the workpiece edges and a consumable guide tube, which delivers additional filler material. The molten metal is contained by a water-cooled copper dam, allowing the weld to solidify as the trough moves upward. Fundamentals of ESW. Principle: a pool of molten slag covers the weld pool and provides energy for the welding process. Mechanism: once initiated, the process relies on joule heating of the slag to maintain the weld pool temperature. Applications: ideal for heavy structural components, bridge segments, and large machine bases. Equipment setup and operation for ESW. Power source typically uses high current power supplies to sustain the process. Consumable guide tube acts as both an electrode and a source of filler material. Copper shoes: water-cooled shoes confine the molten slag and weld pool. Travel system: mechanized movement of the welding head and cooling shoes along the joint. Effective operation of ESW requires precise control of startup parameters, constant monitoring of the weld pool, and ensuring uniform travel speed to prevent weld defects such as porosity or inclusions. Advanced techniques in ESW. Narrow gap ESW reduces weld metal volume and heat input, minimizing distortion. Hybrid ESW combines ESW with other welding methods to optimize weld properties and efficiency. Automation, implementation of robotic systems for consistent quality in large-scale repetitive tasks. Safety in ESW. PPE, extensive use of personal protective gear to safeguard against radiant heat and spatter. Fire safety, implementation of fire-resistant barriers and readiness with fire extinguishers. Slag handling, proper disposal and handling of slag residue are crucial to prevent contamination and accidents. Executive summary. Here's a summary of specialized welding processes and applications. Specialized welding processes. 1. Laser beam welding (LBW) uses a high-energy laser beam to melt and join metals. 2. Electron beam welding (EBW) uses a focused beam of electrons to melt and join metals. 3. Friction stir welding (FSW) uses a rotating tool to generate heat and join metals. 4. Ultrasonic welding (USW) uses high-frequency vibrations to generate heat and join metals. 5. Resistance spot welding (RSW) uses electrical resistance to generate heat and join metals. Applications of specialized welding processes. 1. Aerospace industry. LBW, EBW, and FSW are used for welding lightweight materials such as aluminum and titanium. 2. Automotive industry. RSW and USW are used for welding body panels and other components. 3. Medical device industry. LBW and EBW are used for welding medical implants such as hip replacements and surgical instruments. 4. Energy industry. FSW and EBW are used for welding nuclear components and other high-performance materials. 5. Aerospace and defense industry. LBW, EBW, and FSW are used for welding advanced materials such as composites and smart materials. Benefits of specialized welding processes. 1. Improved quality. Specialized welding processes can produce high-quality welds with minimal defects. 2. Increased efficiency. Specialized welding processes can increase productivity and reduce production time. 3. Reduced distortion. Specialized welding processes can minimize distortion and maintain the integrity of the workpiece. 4. Enhanced material properties. Specialized welding processes can enhance the material properties of the workpiece, such as strength and corrosion resistance. 5. Cost savings. Specialized welding processes can reduce production costs by minimizing material waste and reducing the need for post-weld processing. Here's a summary of submerged arc welding saw and electroslag welding ESW. Submerged arc welding saw. Definition: saw is a welding process that uses an electrical arc to melt and join metals, with the arc submerged under a layer of flux. Key features: 1. High deposition rates. Saw allows for high deposition rates, making it suitable for thick plate welding. 2. Deep penetration. Saw can achieve deep penetration, making it suitable for welding thick sections. 3. Good mechanical properties. Saw produces welds with good mechanical properties, including strength and toughness. For low hydrogen content, saw produces welds with low hydrogen content, reducing the risk of hydrogen-induced cracking. Applications: 1. Shipbuilding. Saw is widely used in shipbuilding for welding thick plate sections. 2. Heavy equipment manufacturing. Saw is used in heavy equipment manufacturing for welding thick plate sections. 3. Construction. Saw is used in construction for welding thick plate sections such as in bridge building. Electroslag welding ESW. Definition: ESW is a welding process that uses an electrical arc to melt and join metals, with the arc submerged under a layer of slag. Key features: 1. High deposition rates. ESW allows for high deposition rates, making it suitable for thick plate welding. 2. Deep penetration. ESW can achieve deep penetration, making it suitable for welding thick sections. 3. Good mechanical properties. ESW produces welds with good mechanical properties, including strength and toughness. 4. Low distortion. ESW produces welds with low distortion, making it suitable for welding large or complex structures. Best practices. 1. Regular maintenance. Regular maintenance must be performed on the welding equipment to ensure that it is functioning properly. 2. Proper training. Welders must receive proper training on the operation of the welding equipment and the ESW process. 3. Quality control. Quality control measures must be implemented to ensure that the welds meet the required quality standards. 4. Documentation. Documentation must be maintained on the welding process, including the welding parameters, equipment settings, and quality control measures. Here's a summary of advanced techniques in Electroslag welding ESW. Advanced techniques in ESW. 1. Pulsed ESW. This technique involves pulsing the welding current to improve weld penetration and reduce heat input. 2. Variable polarity ESW. This technique involves switching the polarity of the welding current to improve weld penetration and reduce porosity. 3. Hot wire ESW. This technique involves feeding a hot wire into the slag pool to improve weld penetration and reduce heat input. 4. Narrow gap ESW. This technique involves welding in a narrow gap to improve weld penetration and reduce heat input. 5. Automated ESW. This technique involves using automated systems to control the welding process and improve weld quality. Benefits of advanced techniques in ESW. 1. Improved weld quality. Advanced techniques in ESW can improve weld quality by reducing porosity, lack of fusion, and other defects. 2. Increased productivity. Advanced techniques in ESW can increase productivity by reducing welding time and improving weld penetration. 3. Reduced distortion. Advanced techniques in ESW can reduce distortion by minimizing heat input and improving weld penetration. 4. Improved material properties. Advanced techniques in ESW can improve material properties by reducing residual stresses and improving weld microstructure. 5. Cost savings. Advanced techniques in ESW can reduce costs by minimizing material waste and reducing the need for post-weld processing. Challenges and limitations of advanced techniques in ESW. 1. Equipment costs. Advanced techniques in ESW may require specialized equipment, which can be expensive. 2. Operator training. Advanced techniques in ESW require specialized training for operators, which can be time-consuming and costly. 3. Process complexity. Advanced techniques in ESW can be complex and require careful control of welding parameters. 4. Material limitations. Advanced techniques in ESW may not be suitable for all materials, and some materials may require specialized welding techniques. Future developments in ESW. 1. Increased automation. Increased automation of the ESW process is expected to improve weld quality and productivity. 2. Advanced sensors and monitoring systems. Advanced sensors and monitoring systems are expected to improve process control and weld quality. 3. New materials and applications. New materials and applications are expected to emerge, requiring advanced ESW techniques and specialized equipment. Conclusion. Both submerged arc welding saw and electroslag welding ESW offer unique advantages for industrial applications where high deposition rates and robust weld quality are paramount. By understanding the fundamentals, operational setups, advanced techniques, and safety protocols, professionals can effectively leverage these welding processes to achieve superior results. Thank you for participating in this lesson. We hope this knowledge serves as a valuable resource in your welding journey. Happy welding and happy learning. See you again in the next lesson.